And I'll start with some notation. So K will always be a field of characteristic 0. And I fix an algebraic closure K bar. And I will consider the absolute Galois group, gamma, or gamma K, if there is an ambiguity, is the absolute Galois group of K. And K will often be a number field. Because I'm interested in finding rational points on varieties or give necessary cohomological conditions on varieties for the existence of a rational point or the density of rational points for the adelic topology. So I'm going to explain this later. And I will start with the review of Nonabelian cohomology. This is going to be the first part of my talk. So, review of Nonabelian Galois cohomology. So maybe I can give a reference for this. An outstanding treatment of this topic is Serre's book. So, Galois cohomology. So it's part 1, chapter 5, or if you understand French, cohomologie galoisienne. So I fix the field K, and I'm going to consider algebraic groups over K. So let G over K be an algebraic group. So usually I'm going to assume that G is linear. That is a closed subgroup for Zariski topology of some GLN. But I'm not going to assume that G is connected. So not necessarily connected. And we will see that, for example, the case when G is finite is going to be very interesting. This is for giant, I suppose. Okay. And so if I take such an algebraic group, I can consider G of K bar, the set or the group of K bar points on G. And G of K bar is equipped with, let's say, the left action of the Galois group, gamma. So I'm going to define Galois cohomology for this situation, gamma, the Galois group, acting of the K-bar points of G. And here I consider left action. It's important because Later on, I'm going to consider torsors, so actions of algebraic groups, and I will take right actions for torsors because I want both actions to commute in a certain sense. Maybe I can give some examples of groups. So the first case is an important one. It's a case of a finite group. So this means that G is finite, if you prefer, as a scheme over a spec K. So this does not mean that G of K is finite. This is not sufficient. This means that G of K bar is finite. And giving such a group, it is equivalent to giving G of K bar as an abstract finite group plus an action of the Galois group gamma So, for example, you can take G equals to Z mod n. This means that you consider the cyclic group with n elements with the trivial action of G. But you can also take, for example, G equals to mu n. This means that you consider the group of n roots of unity in K bar with the natural Galois action of gamma. So this is the same as a group, but not as a group with the action of gamma. For example, notice that if you take for K the field of rational number and G is mu3, then mu3 of Q, the group of rational points, is just 1. But over Q bar, of course, you recover the cyclic group with 3 elements. So this is the first example, finite group. Second important example that was probably discussed last week is the case of a torus, a K torus. So this means that over K bar, if you consider G bar, which is by definition G over K bar, is isomorphic to some copies of the multiplicative group, to Gm to some power. So G bar is Gm to some power, but only over K bar. So if G is just a Gm to some power, it is a split torus, but you can have non-split torus. For example, consider this equation, y to the square minus az to the square equals to 1, where A is a non-zero element of K. It is a torus of dimension 1. But it is not isomorphic over K. So it is not isomorphic to Gm, to the multiplicative group, if A is not a square. So usually this torus is denoted by R1 of capital K over K of Gm, where capital K is just K of square root of A, because it is the kernel of the norm map So here, this is an example with a commutative group, connected and commutative group. I really don't understand how it works. Sorry? Good question. No. Yes. But is there a solution to? I'm too short. I'm too short to do this. Okay, but okay. I see. Because here there is nothing I can do. Okay, now we can see some non-commutative examples. For example, G equals to PGLN. So this one is semi-simple. Or G can take SLN. And this one is not only it is semi-simple, but it is simply connected. If you want to check these properties, you can just go to the algebraic closure K bar, or if you assume, for example, that K is a number field, just embed your number field into C and check these properties over C. And we shall see later that for descent over number fields, semi-simple, simply connected groups are not very interesting. I'm going to explain why later. Okay, so these groups are non-commutative and they are connected. And here is an example with a non-connected group. If Q is a quadratic form, over K, then you can consider the orthogonal group of Q, of this quadratic form. And so this one is not connected. And so I assume, of course, that this quadratic form is not degenerate. And I have an exact sequence with the special orthogonal group. It goes like this. So it is an extension of a very small group, finite and abelian group, by a connected group. Okay, so now I'm going to define the homology set. Is there anything better? Because oh, good. So H0 is easy. H0 of Kg. So by definition, it's H0 of the Galois group acting on G of K bar. So this is just the group of k-bar points invariant by the action of Galois. That is just the group of k-rational points of the group G. So after H0, there is an H1, but unlike the commutative case for G, in general, there is no H2, H3, and so on. And H1 of Kg, so if you prefer, it's H1 of gamma acting of G of K bar. So if G is not commutative, it is not a group, it's just a pointed set. So a set with distinguished elements. So not a group in general, if G is not commutative. So if G is not commutative, there is no fancy definition with derived functors, homological algebra, and so on. So it's just a definition by cocycles. So by definition, H1 of Kg quotient of Z1 of Kg by an equivalence relation. So Z1 of Kg is the set of cocycles. So it's a definition very similar to the usual definition for commutative groups. It's defined of the set of map from the Galois group gamma to G. And I have to assume that this map is continuous. So to G of K bar, sorry. So what does it mean continuous? Here G of K bar is discrete. And gamma is equipped with this profinite group topology because gamma is the inverse limit of the Galois groups at a finite level. And there is the cocycle condition, which is f of gamma 1, gamma 2 must be f of gamma 1 multiplied by gamma 1 acting on f of gamma 2. So this means that I take f of gamma 2, this is an element of G of K bar, I take the action of gamma 1 on this element, and I multiply by f of gamma 1. Of course, here you have to do this in the right order because the group G is not assumed to be commutative. So if G is commutative, you recover the usual additive definition. F of gamma 1, gamma 2 is f of gamma 1 plus gamma 1 acting on f of gamma 2. And what is the equivalence relation? F is equivalent to G if and only if there exists an element B in G of K bar such that f of gamma is G of gamma twisted in some sense by B. So here you put B minus 1. And here you put gamma acting on B. So once again, in the commutative case, you recover the usual definition. So for example, if the action is trivial, gamma acts.
This is a different B depending on which gamma you have?
What?
So this is depending on gamma?
For all gamma, sorry. This means that f and g differs by some twist by the cocycle B. So if gamma acts trivially, this set H1 of Kg is just the homomorphism, the continuous homomorphism from gamma to G of K bar up to conjugation. Conjugation in G of K bar, of course. So I told you that there was a distinguished element. So what is the distinguished element? So it is usually denoted by 0. H1. So it's just the class of the trivial cocycle. So from gamma G of K bar, sending anything to the unit element. So now H1 of Kg is a pointed set. And before explaining the properties of this pointed set, I want to give another definition using torsors. Because the new definition maybe is easier to understand when we deal not with the spectrum of a field, but with cohomology over a variety. So it's related to the notion of torsors. Let's say G torsors over K. I should say over spec K. So what does it mean? So G torsor, or you can say a principal homogeneous space. In this situation over K is a non-empty set A equipped with the left action of the Galois group and the right action of G of K bar so here it's important to take a right action of G of K bar, and this right action has to be simply transitive. So simply transitive means that if you take two elements, there is one and only one element of G of K bar sending the first one to the other one. And of course, these both actions have to be compatible. So what does it mean, compatible? So this means that if you take gamma acting of x point G, it's gamma of x and gamma of G acting on gamma of x. So here gamma is an element of gamma, x is an element of A, and G is an element of G of k bar. And as a matter of fact, isomorphism classes of these objects correspond to the first Galois homology set. So let's make it a proposition. What? That's a good question. Actually, not for Galois homology, but in this setting, if you take such a set A, you can take the quotient of A by the action of the Galois group, and you obtain a variety. I'm going to explain this. So all these torsors in this setting are representable by a variety over K, a K form of the group G. So I was going to explain this later. So proposition, the set H1 of Kg, you can say first homology set, but there is no second one anyway, in general. Corresponds to isomorphism classes of G torsors over K. By the way, instead of G torsors over K, you can say K torsors under G. Sorry?
What's a morphism of torsors?
Well, you take the obvious definition. So you must have a map that is compatible with both actions. In this setting, yes, between the set, but compatible with both actions. But as a matter of fact, in this situation, there is really an equivalence of categories between these principal homogeneous spaces and torsors in the sense of the algebraic geometry. So I didn't want to go into this.
The category of G torsors would be a group?
Yes. In this setting, yes, because the group G comes from a linear algebraic group. So it's affine over a field. So in this situation, there is no problem. If you work, for example, with, I don't know, abelian schemes over an arbitrary scheme, then it's no longer true. But in this setting, there is no representability problem. Maybe I'm going to explain this later. Okay, I'm not going to give details, but I just want to explain where the bijection comes from. So if you take a cocycle, let's say C is a cocycle, then you can define a K torsor A under G. So I've switched notation. So as follows, you take A is G of K bar as a set, but the Galois action is twisted with a new Galois action and the new Galois action is defined as follows. Gamma acting on X, you take the former Galois action, gamma of X, and you twist with the cocycle C, C of gamma, multiplied by gamma of x. So it's the same set, but with a new Galois action. So in particular, A is representable by a K variety. You just take x, the quotient of this, by gamma for the new action. Because any group variety over a field is quasi-projective, so you can take the quotient by a continuous action. And of course, you have to check, but this is not difficult, that this does not depend, that the class of isomorphism of U torsor does only depend on the cohomology class of C, and so that you have a well-defined map. And the other way, so the other way it goes like this. If you take A G torsor, so you choose a point x0 in A, and for each gamma in the Galois group, if you take gamma acting on x0, this is a new point on A. So because the action is simply transitive, there is a unique C of gamma such that this condition is fulfilled. And you check now that the map gamma C gamma is a cocycle, and that its cohomology class is well defined. This means if you change the point x0, you get the same cohomology class, and if you change the torsor, but it's in the same isomorphism class, then you go the same cohomology class. So that's why you have both definitions for definition of H1 of Kg. Okay, now we can list some properties. So some of the properties are easier to check with the first definition, the definition with cocycles, and some of the properties are easier to check using the torsor definition. So the first one is about functoriality. So it's covariant in G. This means that if you have a map like this of K groups, morphism of K groups, of algebraic groups over K, then you have a map from H1 of Kg to H1 of Kh. So this property is very easy to check using cocycles. And when I say a map, I cannot speak about a morphism because these are not groups, but this means a map of pointed sets. So the distinguished element goes to the distinguished element. So it's covariant in G, but it's contravariant, well, not in K, but in spec K. Of course, I could say covariant in K. So this means that if you have an embedding of fields like this, then you have a map from H1 of Kg to H1 of Lg. This means here that this is H1 of L with values in G of L bar, an algebraic closure of L. I prefer to say contravariant in spec K because in the next section, K will be replaced by a scheme, a variety. So it's contravariant in the scheme here. And for example, this property of contravariance is easier to check if you use this definition, because if you have x over k G torsor, then you can just take the pullback x cross k L, and you obtain a G torsor, but over spec L, not over spec k. And the second very important property is the behavior with respect to short exact sequences. So if you take a short exact sequence of k groups, so exact sequence of k groups, this means that the corresponding sequence of abstract groups is exact, but you have to take k bar points. That is G1 of k bar, G2 of k bar, G3 of k bar. 1 is exact. Of course, it does not say that it is exact if you replace k bar with k, because we don't work over a closed field. Then there is a long exact sequence. Well, long, it's quite short actually. It's long if you work with commutative groups. But you have an exact sequence anyway. So like this, 1, G1 of k. So if you prefer, this is just H0, G2 of k, G3 of k, H1 of k, G1, H1 of k, G2, H1 of k, G3. But it is just an exact sequence of pointed sets. This means that the image of one map is the kernel of the following. Kernel makes sense because these are pointed sets. But for example, a map can have a trivial kernel and not be injective. This is possible because these are not groups, just pointed sets. And there is a special case if G1 is central in G2, so if G1 is contained in the center of G2, then the sequence can be extended, but only with one term, with H2 of K G1. But assuming that G1 is abelian is not sufficient. You have to assume that it is central. And once again, you just get a map of pointed sets, not homomorphisms, even if this group and this group both are abelian. So you have to be very careful with exact sequences of pointed sets. Okay, so let's see some examples. So the first case is with the GLN or SLN. So H1 of KGLN is 0, as well as H of K SLN. This is the famous Hilbert-90 theorem. Another interesting case is a special case of the so-called Serre's conjecture 2. If K is a local field, then H1 of Kg is 0 if G, local field means a finite extension of QP, non-Archimedean local field. So if G is semi-simple and simply connected, so I think this is due to Kneser. And you have a similar result for number fields. H1 of Kg is 0 for a, so similarly, for a totally imaginary number field. Yes?
What do you mean by simple connectedness?
Simply connected, you can check this over C if you prefer. Embed your field to C, and this is the usual definition. All this means that there is no non-trivial isogeny for another group to this group. So for example, SLN or spin, and similarly for a totally imaginary number field. So that's why for descent, these groups will not be interesting for us. And finally, an example with a central extension. So consider this short exact sequence, GM, GLN, PGLN 1. So if you take homology, H1 of K GLN is 0, this is Hilbert 90. So you obtain a very short exact sequence. H1K PGLN goes to H2 KGM, and this is just the broad group of K. And as a matter of fact, this is always injective. And if you take the union of all these for miscellaneous n, then you obtain the whole Brauer group, because this is the cohomological Brauer group, and this corresponds to a central simple algebra of degree n. So this is a general theory of central simple algebra. It's classical that both definitions of Brauer group agree. Okay, so now I'm going to extend this construction over an arbitrary variety. So this is the second part of my talk. So I consider X over K an algebraic variety. And just to make things simpler, I will always assume that X is projective, smooth, and geometrically connected. And now I can define a cohomology set H1 of X G. And once again, there are two definitions. Either you take cocycles, but then you have to consider Čech cocycles and even Čech cocycles for étale topology, because we know that Zariski topology is much too coarse to define, for example, Galois cohomology over a field. Or you can consider isomorphism classes of torsors, so right torsors, let's say X torsors under G. So this means that there should be an action of G on X that is simply transitive in the geometric fiber and now you have exactly the same properties. Sorry? Oh, yes, sorry. Thank you. Yes, this is definition of a torsor Y. So let's call.
What's the definition?
Sorry? Where? No.
It's the definition for the torsor of X.
So this is okay. X action or so Y over X under G is a torsor. This means that there is an action of G on Y compatible with this map and which is simply transitive in the geometric fibers. So they are the same functorial properties. So in particular, if you have a map from x prime to x, then you have a map from h1 of xg to h1 of x prime g. You take the class of a torsor y and you send it to the class of the fiber product, like this. And one special case of this construction is especially interesting. Is if you take the evaluation on a rational point, I'm afraid not. No, I'm too short to do that. Okay. Okay. So now take a point, a rational point on x. Then you can take, so if you take a g-torsor like this, you can take the evaluation so you take the class y of the torsion in h1 of xg, and then you take y of m. It's an element of h1 of kg. Just use the morphism from spec k to x given by this rational point. It's just a special case of this construction. And in particular, saying that y of m is 0, this is equivalent to saying that the fiber ym, let's call this f, so this is the inverse image of m, has a k point. Because, yes, I should have said that before, a torsor is trivial in general. This is equivalent to saying that there is a section. So now I can give a descent statement. Because I can refine this observation. So more generally, saying that y of m is the class of some cocycle C, so C is a cocycle, this is equivalent to saying that the so-called twisted torsor y sigma, yc, sorry, satisfies yc of m is 0. So what is the twisted torsor? Yc is another torsor over x, is defined as follows. So in general, it's no longer a torsor under C. But under a twisted form of G. say GC. So GC is an inner form of G. GC over K bar is the same as G over K bar. But there is a twisted Galois action. So the new action, gamma on an element of G, you take the former action and you take a conjugation by the cocycle like this. So this is the new Galois action. And the new torsor, the twisted torsor, is defined as follows. So the twisted torsor YC over K bar is the same as Y, but there is a new Galois action. Gamma acting of Y. You take the former action and you multiply by C gamma to the power minus 1. So this is an element of the group G, G of K bar, that acts right action on the K bar points of the torsor Y. So now if you use this statement and U statement, you obtain the disstate statement. That X of K is the union for all homology class or homology classes of the image of the rational points of the twisted torsors. So for the twisted torsors, you call F of C the map of white C to G. So just using this and this, any k-rational point on X is obtained as the image of a rational point on some twisted form, YC, of the initial torsor Y. So in the abelian case, the twisted group GC, this is X, sorry. GC is just G. And you can say what the class of the twisted torsor is. The class of YC is just the class of Y minus the class of C. Because C is in H1 of KG, you can push it by functoriality to H1 of XG. And in the abelian case, you can take the difference because in the abelian case, you have an abelian group for H1 of XG. But in general, if G is not commutative, this does not make sense. So this is a substitute for this notion. And now the last thing I want to explain is the extension of the descent statement with adelic points. This is bad. Oh, this is really too difficult to use. Sorry. Sorry?
So under what conditions do you have this statement?
This statement? You just assume that you have a torsor Y over X under G. There is no other assumption.
So particularly if H1 is 0, then there are no rational points?
If H1 is 0, this means that as soon as you have a rational point on X, you have a rational point on Y lying over this rational point. Now this means that this construction is not very interesting for groups like SLN or more generally for a semi-simple, simply connected group. Because here is the main interest of this construction. So now, this is true over any field of characteristic 0. So now assume that K is a number field. And consider KV, this completion. You just have X of AK is the product for all V of X of KV. So the set of local points. And now you can say that X of K is a subset not only of the set here, but of the union over any cohomological class of the image of the adelic points on the torsors here. So this is obvious because a rational point gives an adelic point. And call this set X of AK to the power F. So this is a subset of X of AK. And using the previous construction, it's very easy to see that this is just the set of PV in the set of adelic points, such that if you take the evaluation Y of PV, so this is an element in the product of H1 KVG, and I demand that this is a global class, so this is in the image of H1 of KG, like this. So this is exactly the same, asking that there is an adelic point of some YC lying over the rational point, or that if you take the evaluation of the torsor Y on the adelic point PV, it's a global class. And so now we have a necessary condition for the existence of a rational point. One of the torsors, the twisted torsors YC, must have points everywhere locally. So probably you saw this statement for an abelian group or group of multiplicative type G, for example, a torus last week. This is an extension of this statement. And what I will explain tomorrow is that if you use general groups G, for example, finite but not commutative groups, you can refine the Breuer-Manin obstruction using this construction. The Breuer-Manin obstruction essentially corresponds to the case when G is a group of multiplicative type, that is the extension of a finite abelian group by a torus. So I will explain tomorrow how to use this set. Thank you.